Hey everyone, welcome back to the I'm way too deep in water simulation to give up now channel. Today, we're diving into how I finally got my water simulation working at more than 3 frames per second. Here's what's coming up. The journey from super complex fluid algorithms that broke my computer to something actually usable. The simplified cellular automaton approach that saved my sanity, the chunk implementation that scales to entire worlds, sneak previews of some work in progress features, and my vision for a natural water ecosystem with streams, rivers, and lakes. So if you enjoy watching a mediocre programmer with delusions of grandeur try to build an entire ecosystem, grab your popcorn and let's get started. I'm not gonna lie, I've been going through a cycle of it's so over, we're so back for a while now. At times, I've been getting really disillusioned with the status of this project, but eventually I kept pushing through it and here we are with another update.
What is he doing?
He's beginning to believe.
I realized that I never actually talked about the game I'm planning to make and why I'm going through all this trouble to create a cohesive water system for it. So make sure to stick around until the end to find out more. Last time, I showed you this monstrosity. A full 3D fluid simulation based on actual computational fluid dynamics papers that I definitely understood completely and didn't just copy paste while nodding knowingly. It had conjugate gradient methods, multigrid solvers, and other words that make me sound smart, but actually resulted in this. My computer was literally begging for mercy. I'm pretty sure my GPU started drafting its resignation letter. Meanwhile, I needed something that could simulate water across an entire procedurally generated world without requiring a NASA supercomputer. So I did what any reasonable game developer would do. I threw out 90% of my code and started over with something simpler. Here's the basic idea I implemented in the simplified version of the fluid simulation class. Instead of solving complex 3D fluid equations, we're now using a cellular automaton approach combined with a height field method. Each cell in a grid keeps track of how much water it has, how much water is flowing to each of its 6 neighbors, whether it contains terrain, aka collision, and whether it's settled, so not actively changing much. The core simulation loop is deliciously simple. Basically, it will calculate how much water wants to flow out of each cell, move the water between cells based on those calculations, and update our list of active cells for the next frame. The physics is actually super simple too. Water flows downhill due to gravity. I know, shocking concept. It spreads horizontally based on pressure differences. It can flow upward when enough pressure builds up, and it can settle when it's stable enough. The simplified approach worked great for small areas, but I wanted entire rivers, lakes, and oceans. That meant building a whole new system using chunks. Here's the core idea from my chunk fluid simulation class. Each chunk is responsible for a 16 cube grid of cells by default, but only chunks near the player are actually loaded and simulated. This means we can have a theoretically infinite water system while only processing what's visible. The dynamic loading system is pretty cool as well. The real magic happens with cross-chunk water flow. When water reaches the edge of a chunk, it needs to seamlessly flow into the neighboring chunk, like so. Here's where it gets really interesting. I implemented a ton of optimizations to make this run smoothly. The first one is the level of detail. Distant chunks update less frequently and with simpler physics, while chunks right around you get the full simulation. Second optimization was multi-threading. Each chunk can simulate independently on different CPU cores, massively boosting performance. The third one is making fluids settle, so cells that haven't changed much for a while are marked as settled and get skipped in expensive calculations. The next one was a more efficient cell format. By compressing the cell data format, we can fit way more cells in memory and improve cache efficiency. The current state of the simulation is this. Our current implementation can flow realistically across terrain, so water properly flows downhill and around obstacles. It forms pools and lakes, so the water accumulates in depressions and forms flat surfaces. It simulates sources and sinks, so we can add water from springs or remove it through drain points. And now it scales to huge worlds. With the chunked system, we can simulate water across entire landscapes. All of this runs in real time and can be scaled to handle larger areas through the chunking system we've implemented. Now that the water actually works without setting my computer on fire, I can start building the interconnected ecosystem I've been dreaming about. Here's a sneak peek of a work-in-progress erosion system. Water doesn't just flow over the terrain anymore, it actually shapes it. Over time, flowing water carves channels and deposits sediment, creating natural-looking stream beds and river valleys. Here's where I'm going with all of this. Do you know those YouTube videos from Annie Austin where he goes and tracks where the river come from, where did they go? I want to create a cohesive water ecosystem where springs emerge from mountainsides, streams form and join together, rivers carve their way through valleys, and lakes form in depressions, wetlands develop in floodplains, and eventually everything flows to the ocean. The player will be able to interact with the system at every level. Build a dam, the water redirects. Dig a channel, create a new stream path. Cut down forest, erosion increases and terrain changes over time. The whole system will be persistent and simulation based rather than just visual effects. The stream isn't just a particle effect, it's actual simulated water that can be collected, redirected, or used to power mechanisms. So what's coming up next for our aquatic adventure? The most immediate focus is getting this working at a larger scale so we can generate entire river networks across our procedural world. This journey has been a perfect example of game development reality. Start with an overly ambitious idea, implement the most complex solution possible, watch your computer beg for mercy, and then finally admit defeat and do what you should have done from the start. But honestly, I don't regret the detour through overcomplicated algorithms land. I learned a ton, and that knowledge still helps me make better decisions with the simplified system. The key lesson: it doesn't matter how mathematically perfect your simulation is if your game runs at PowerPoint presentation speeds. I already talked about the water ecosystem and how it affects gameplay, and I'll go into more details about the vision for the game, its motivation, and a few other details probably in the next video. I'm most likely going to work on the renderer for the water system to make it look a bit nicer, work some more to create the quote-unquote static water of our world, and probably going to move on to other areas of development for now, as I'm starting to notice burnout with the complexity of the water system. If you enjoy watching me struggle through fluid dynamics and pretend I know what I'm doing, make sure to like and subscribe. Next time, we'll be expanding our water system across the entire world and adding more ecosystem features. Until then, stay hydrated, and remember, in game development, good enough that actually ships is better than perfect that never does. See you in the next one.